Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, today we will continue talking about processing or dealing with features, and then I hope that we will have good time to start talking about evaluation, which is still in the practical issues session. What was the last thing that we covered last time? We're talking about irrelevant features and redundant features, right? We're talking about trying to remove, or we thought about the issue of redundant features and whether a specific model can be affected by these kind of features. Today, inshallah, we'll talk about how to remove complete features or change the values of the features, okay, so that it will be easier for learning. So the first thing is called feature pruning. Feature pruning means that we will remove some features. Right. Based on what? Let's say that we start with the easiest case, which is binary features. Okay, so in binary features we have either 0 or 1 as values, right? Let's say that we found a feature that is always 1 in all examples. Will that be useful feature or not? It's always 1 in all examples. Yeah, which means that it exists because it's binary, right? We can say it exists in all examples. Would that be useful? Why not? Yeah, because it doesn't distinguish between the positive and negative examples, right? It's always there. Okay? Same case when we have all zeros or almost all zeros, right? So in this case, it doesn't exist anywhere, so it's useless. Type maybe we can just leave it in the training data, but removing it first will reduce the time of processing of learning. Okay, instead of all the features, we can just remove some of these features. Will save us some time. And also some of the learning algorithms might be confused with these features, so it's better to remove them. Examples for that, the word "the" almost appear in all documents, right? So removing it should not harm the classification. On the other side, misspellings. If there is a word that was misspelled, maybe it will appear in 1 or 2 documents out of thousands or sometimes millions. Okay, so maybe also we can remove them. So these are examples of that kind of features. So it is much easier in case of binary features. Okay, binary features that has just 2 values, true or false, or exist or doesn't exist. Right. What happens if we, and the idea here, let me emphasize on that. The idea is that the feature will have almost constant value. Okay, so if the feature has constant value over all the examples, then it will not be that useful. Okay, so that's the main idea. Right. Now, if the features are real valued, if we have a real value for the feature, okay, so it's not 0 or 1. We cannot say it exists or doesn't exist in the examples. We will see different real values. Type. If we think about the idea of having almost constant value, how can we see that when we have a real value feature? Yeah, when can we say that this feature has almost constant or very small range? How can we compute that? How can we characterize that? How can we say, yes, this value, this feature don't change much? Do you remember something in statistics that we can use? Do you remember statistics?
I don't get what you're talking about.
Okay. Type. For binary features, we said that if the value of the feature is almost always constant, is almost always have the same value, then it's useless, right? Because it doesn't change across different examples. Type. This is easy when we have 0 or 1, right? It's either 0 or 1, two possible values only. But for real value, like GPA, GPA can have a very big range, right? It's, although from 0 to 4 it's not very big, but the possible values are infinite, right? So we cannot actually, we cannot actually talk about constant anymore, okay? We have to be a bit flexible. So in real values, if these real values don't change much, okay, then maybe we can say that it's useless, right? But the question now is, how can we say that it doesn't change much? How can we know that it doesn't change much? Remember, in statistics, we have something called standard deviation or variance, right? Okay, the standard deviation. If the standard deviation is large, what does that mean? It changed a lot, right? There is lots of variation in the values, right? If it's very small, then it is the range of variation is very small, so we can think of it as getting towards being constant, right? So the idea here is that we will look for features with low variance. If the feature has low variance, that means it doesn't change a lot. So we can consider it as constant or towards being constant and just remove it. Okay? So we can, in case of binary features, we can count. We can say 99% of the examples have this feature. Have this feature means the feature value is 1. Or 99% doesn't have this feature. Okay? But for real valued features, we cannot do that. So we can compute the variance for each feature, and the feature that has very low variance, that means it doesn't change a lot across different examples, and thus probably it is useful. It is useless. Okay? Did you get the idea here or not? Any question about this? Right. When we say look for features with low variance, so we will remove the low variance features, or we will keep the low variance features? We'll remove, because low variance means they have, low variance is something like that, right? Sorry. A very low variance, right? But something like this, as a distribution, variance is much larger, right? And if that gets smaller and smaller, that means that it maybe is just one or very few values. Okay? Right. Now we'll switch to, so here we are removing complete features, right? So we say, okay, this column, which is this feature, is useless. So we just remove it, and then we can do the learning without this feature. Right. Here we will talk about normalization. So what do you mean by normalization? Have you heard about this word before? Normalization? What do you mean by normalization?
Normalization is to convert any real value into a value between 0 and 1.
That's an example, but that's not always the case, but the idea is to change the values so that they can be comparable, they can be compared. Maybe they have the same scale, same range, things like that. Okay, so normalization means changing the values to new values, and then in the new values, different values will be comparable, will be similar to some extent. Okay? Fine. Why is that a problem? Remember in KNN, when we talked about the example of having the salary and the height of the person, okay? And so the scales are completely different, right? And with KNN, for example, when we have different scales or different variation of scales, that will be a problem, right? Because KNN deals with all the features equally. It assumes that all the features have the same importance. So with the value of the feature, high will be high, it will affect the distances, right? So it's better to do the normalization before that. So that's one example. Type. There are many different ways of doing this normalization. There are two types actually. If you envision the training data to be like this, if we have every line here is an example. So this is example 1, example 2, and so on. And the columns are the features. So these are features, and these are examples. So rows are examples, and columns are features. Okay? Then normalization is having two types. The first one is called feature normalization, which will deal with columns, with complete columns. So we'll change the values of a complete column, which means that changing the feature value for every example, for one feature. Okay? That's what we mean by feature normalization. And the other type is called example normalization. This one deals with individual examples. So in this view, it is applied on rows, not columns. Okay? Is that clear? So feature normalization is done on features. Example normalization is done on examples. So one is done on individual features across all examples, and the other is done on individual examples across all features.
So what was example again? Feature value.
Example in training set. The training set has multiple examples, right? Multiple labeled examples. That's what we mean by example.
Then this example has features.
Of course, yes. Each example it's like a feature value. Yes.
So if we do the example, like what's the difference?
Yeah. We will talk about the details. Yeah, but I'm just telling you that there are two ways of doing the normalization. Okay. One is applied on the features, and the other is applied on the examples. Okay. Now let's talk about each one. So we'll talk about feature normalization, and all of what we will actually talk about are feature normalization except one. Okay. So the first one is called centering. What do we do in centering? Let me first explain the notation here. So x is an example. N is the number of the example. So xn is the example number n. Okay. And then d is the specific feature. Okay. So here we are changing. Remember, normalization will make changes to the values of the features. So here we are changing the feature number d in example number n. And of course, we can apply that on all the examples. Right. What are we doing in centering? It's by the name. We are centering everything to the origin, to 0. Okay? So after this normalization, all the centers of the features, if we do that on all features, will be 0. How can we do that? We'll just subtract the mean of the feature. So if we assume that this is the specific feature here, and we have the examples here, right? So that's the column for the specific feature number D. We will compute the mean of these, and then subtract every value here. Subtract the mean from every value here. Okay? So after doing that, if I compute the new mean, it will be 0. Because we already subtracted the original mean. Right? So that means that we shifted the data from whatever it were to be centered around 0. So if you look at the figure here, let's say that this is the original data. Okay, you see the original data, the brown one or red. And now, after doing the centering normalization, assuming that we have two features, of course, here, right? We have 2D, so we have two features. The center of each feature is 0. So the origin is now the center of the entire data. Okay, so it's like shifting the data to have a center of 0 in all features if we apply that on all features. Okay, even if the data is here, by the way, let's say that the data was here, it will be also shifted to here. Okay, so whatever or wherever the data is originally, it will be shifted to the origin. Type. What's the benefit for that? First, do you understand this? Any question about this? Type. What's the benefit for that? Yes.
I have a question.
Yes.
What's the x and y axis of this graph?
These are two features. X is one feature and y is another feature. And we are doing, for this example, we are doing the centering for both features. Okay? So you see these are different values, right? Different examples. Every dot here is one example. We plot it based on the two features. So you will see that the mean of the x dimension is 0, and the mean of the y dimension is also 0 after centering. Okay, is that clear now? Any other questions on that? Yes.
So we have two means, one mean for each feature.
It's not two means, we have one mean per feature, depending on how many features we want to apply this. For this example, we have two, yes. 2D, right? We have two dimensions. We have two features. So every feature has its own mean value. So we will subtract that mean. That's why we have D here. Okay, so that's the specific feature. So yes, for this example, we have two means. Mean for dimension, the first feature, and the mean for the second feature. Okay, yes.
Sorry, doctor, can you give us an example of the example and the feature? I'm trying to visualize this, but I'm not getting it.
Okay, so let's say x1, x2, x3, x10, and feature 1, feature 2, feature 3, let's say feature 14. Let's say we have 14 features, and we have values here, 0.1, 7.2, -3, and so on. And we have values also in each column. So this is now, let's say that this is 5.3. So this is now the feature vector for example x1. Okay, so here we have just two features. In this example, we have just two features in this figure. Okay, clear now?
Yes.
Any other questions? Okay, now back to my question. I think we didn't answer yet, right? What's the benefit of doing that? Yes.
To have all the features scaled within the origin.
We didn't scale yet, but at least they are around the origin. Okay? They are around the origin, but we didn't scale yet. Okay? We didn't do any scaling yet. And we didn't change the range of the values. We just shifted the values. Instead of being anywhere in the space, all the values now, if we do it on all features, will be around the origin. Okay, so we can compare them. Different examples, they can be comparable. You have a question?
Yeah, I was just wondering, we are normalizing the features?
Yes, now, yes. This is feature normalization.
No, but when you are shifting the examples.
When we normalize the features, this way, if we do it on all features, then we are shifting the location of the examples in the space.
There will be, an example for the example normalization to distinguish.
Yes, of course. We didn't talk about example normalization yet. That's the first feature normalization. Okay. Right, let's see the second one. Right. The second one, this is centering that we saw in the previous slide, right? Right? Right. Now, here we are doing what we call variance scaling. What do we mean by variance scaling? From statistics, remember when we can compute the standard deviation, right? What is the meaning of standard deviation? It gives us a sense of how variable the values are, how different the values are. Standard deviation or the variance gives us a sense of how the values are different, right? How are they distributed? If the variance is large, then they are distributed over a larger range, right? That's the meaning of the variance. Now, if we take the values, a set of values, and we divide each value of them by the variance or by the standard deviation of these values, then the new standard deviation will be 1. That's from statistics. Okay, so if we have all the feature values for a specific feature, we computed their standard deviation. So this is feature number D. Okay, we'll compute their standard deviation, and then we divide every value here by this value. So the new values, after dividing by the variance, their variance will be 1. If we now compute the variance, it's like in the previous slide, when after we do the centering, if we compute the mean, it will be 0, right? Because we centered everything. Here, after we divide by the variance, if we compute the new variance, that will be 1. That means that it's kind of scaling, right? We squeezed, if the variance is very high, then the new values will be squeezed to have a variance of 1. All the features, if we apply that to all features, the variance of them will be 1. So this is a scaling called variance scaling. Okay? Is that clear? Let's look at this example. You will see here that you see the data, the original data are the stars. Okay? And the new, the original values. The new values are the circles. Okay, and you see this is the yellow one became this, and the blue one became this, and so on. Okay. Now we see the variance of this is a bit large, right? You see now the new ones, the variance of them is much smaller. Actually, is 1. But here we did 2 things actually. We did centering first, and then we do the variance scaling. That's why they are now around the center also, around the origin also. Okay, it's not just that they scaled by variance, they are also centered. When we do both, when we subtract the mean and then divide by the standard deviation, this is called z-score normalization. Okay, so here we are doing both in this example, centering and then variance scaling. So if you want to write it in one equation, it will be like this: x in d minus the mean, and then divided by the standard deviation. Okay, so you see now their variance now is much less, and they are moved to be centered by the origin. Okay, is that clear? Any question about this?
So the purpose is to make them shorter,
Not sure.
like to make it towards the center and small.
Centering is making them towards the center. Variance scaling is making them to have normalized, similar ranges. Okay. Now, scaling by the variance will make their variance 1 is 1, so they have similar ranges. Okay. They will not have this original ranges like from 0 to 1,000 or from 0 to 1 million. If you apply that on all these features that have originally different scales, you will have now similar scales. Okay, so you will not have the problem that we saw in KNN. Yes.
But previously, we were studying that having a lantern margin is a better thing that would reduce the error of misclassifying the example. But now we are trying to make them close to each other. What is this?
Say it again.
Previously, we were studying that the more the different examples are drawn from each other, the better. Now we are trying to make them close.
You mean with the dataset, the dataset margin?
Yeah.
Okay, but remember that in what you are talking about, we have positive and negative, right? Here we don't care about positive and negative. When we do this pre-processing, we just care about the scaling. Okay. Yes, the margin might be يعني might change of course, the margin of the data might change of course, but we are solving a problem with the learning model itself, right? So some learning models will not be any good if the scales are different. Okay, so you will have to do this normalization anyway if you choose to apply these models. Okay, did I answer your question? طيب, how many normalization ways we discussed so far? No, 3.
This is the third one?
What are the 2, يا فاطمة?
Plus centering variance
And doing them together is the third one. Yes. Yes. Okay. So centering, variance scaling, and these core normalization, they are different. Okay. But the third one is actually doing the first 2 together. Okay. Right. The fourth one is called absolute scaling. This is easy. Easier than the previous ones. What do we mean by absolute scaling? We just divide the value of the feature by the maximum value of the feature. So RD is the maximum value within that feature. So if we are talking again about feature number D, column number D, we will get the maximum value and we divide by that maximum value. When we do that, what will happen? Yeah, let's say the maximum value is 74. So we divided all the values by 74. What will happen?
Values between 0 and 1.
If they are positive, if they are all positive, then yes, all the values will be between 0 and 1. And not only that, how about the maximum value? Will be 1. Okay, the maximum value will be 1. So how about the minimum value?
0 or if it's positive.
Will it be 0? It doesn't have to. Okay, it depends on what will be the value of the minimum, the original minimum. Okay, we're just dividing by the maximum. So if the minimum is 3, we divide 3 by 70, whatever, 74 we said, or 72. Okay, we divide, it will not be 0. Okay, but the maximum will always be 1 because we divide by the maximum. Okay, so if you look at the example here, you will see that if we do that for all features, which we have 2 here, then the maximum value for the weight will be 1. So this is, I think, corresponding to 1 here. And the maximum value for the price is 1, the second dimension. Okay, so the maximum will be 1, and as you see, all the values now are between 0 and 1. That's because they are originally positive. But if you have negative, you might have something مثلا هنا. It will still be negative. Okay, but at least the maximum value will be 1. That's now scaling. We are now scaling. It's not just the distribution, because with variance we still can have extreme values. Okay, yes, we have the same standard deviation, but still some values might be high. Okay, with scaling, no, we are sure that the maximum value will be 1. Okay, so that's what we mean by absolute scaling. There is also another way of scaling called min-max scaling. So in this case, we subtract the minimum value and then divide by the maximum minus the minimum. Okay, if we do that, yes, Umayya, if we do that, what will happen? Type, what will happen to the maximum value? We subtract the minimum from it and then we divide by the maximum minus minimum. What will we get? 1, right? So the maximum value will be 1, will be converted to 1. How about the minimum value? 0, because minimum minus minimum, it will be 0. So this is the one that will normalize everything between 0 and 1 now. And exact 0 and exact 1. So the minimum value will be 0 and the maximum value will be 1. Okay? So you will see the minimum value here is 0 and the maximum value is 1. Okay? Is that clear? Any questions so far? All of what we discussed earlier was was feature normalization. We are applying these to features. Okay. Now we'll talk about example normalization. We apply this to individual examples. Whole feature vector. Remember examples? We have feature vector, right? This is example number 31. And we have different feature values here, right? One per feature. So we'll take this whole thing and we change it. The most common way of doing example normalization is to make the vector of length 1. So this is a feature vector, right? All the features are numeric. We can see it in the vector space, but the length might be completely different, right? Length of these vectors are different. With example normalization, we will make the length of all examples to be 1. How is that? We divide by its length. You know, you remember the L2 norm length? You know how to compute the length of vectors?
Who is it?
57 years ago. Remember how we can compute the length of a vector? Right? Right. If we divide every, let's say that the vector is x1, x2, x3, and so on. Okay. Now, if we divide every value here by that length, we will get a new vector, right? The length of that new vector is 1. I think you studied that in linear algebra at some point. So if we do this normalization, the length of all vectors now are 1. So that means that if we draw or if we plot the new vectors, all of them will be on the unit circle. So let's see what happens here. So these are the original vectors, right? So this is a vector, this is vector, vector. The length of all of these vectors from the origin, of course, is different, right? Now, if we do this example normalization, all the length will be 1. So all of these points should be on the unit circle. They are not now, right? They are not on the unit circle on the figure here, right? The only reason is that the scales are different. So you see here, this is 1, and here this is 1. So if you draw it on the same scale, you will see that all of them will be on the unit circle. All of them will have the length of 1 from the origin. Okay? So this is called example normalization. All the vectors now are of length 1. Of course, within the dimensions, they might be different. They are not 1. They might be more than 1 or less than 1. But the length of the vector, I can have something like this. Let's say that this is the scaled version, and this is the unit circle. Okay? Right? So let's assume that this is the unit circle. So I can have an example here which has small value on the x on this dimension d1 and high value for d2. And we have also another example that has large value on d1 and small value on d2 and so on. So the different values of features might have different distributions, but the length of all of the example as a vector is 1. All of them will have 1. Okay. One big application of this is when you have different data sets and you want to use the same model. So different data sets might have different scales. Okay, so if you do that, all the examples in both data sets will have the same length, so they are comparable. So you can still use the same model for both of them. Okay? Any questions about this? Right. So we discussed centering, variance scaling, z-score normalization. What else? Absolute scaling and min-max scaling. And all of these were feature normalization, which means that we apply them on individual features. When we say we apply on individual features, we mean apply individual features over all examples. Okay, it's like one column from the data set. Type. The last normalization, it's called logarithmic transformation. This is specific, this is a feature normalization, and this is specific for textual features. Type. What are we doing here? We are changing the values to the log of them. Okay, let's forget about this +1 for a second. So we are taking just the log of the values. Okay, so instead of 8, it will be log 8 to the base 2, which is 3. Okay, 4 will be, ignoring this for now, 4 will be 2, 8 will be 3, 16 will be 4, and so on. Okay, and 2, of course, will be 1. Type. Why are we doing this weird scaling? This is like this kind of scaling, right? But it's not linear scaling. And you are not just dividing by a number. It's not linear scaling. It is logarithmic scaling. We call it logarithmic transformation. Type. Why are we doing this? If I told you we are talking about textual features here, let's say that we have 2 documents. In one, let's say the word Qatar appeared once. In the other, it appeared twice. Okay? So there is a difference, right? Maybe the second one is more about Qatar than the first one. It appeared twice here and once here only. Right? Right? Type. Another case, if we change this 1 and 2 to 10 and 11. So the first document has 10 occurrences of the word Qatar and the other one is 11. Do you think there is a big difference? Although the absolute difference is the same, right? Between 1 and 2, the absolute difference is 1. Between 10 and 11, the absolute difference is 1. Right? Same absolute difference. But it doesn't matter much the absolute difference in the bigger values. So this is like we want the bigger values to have less effect. So we are doing this logarithmic scaling. We are damping the values. We are not taking the values as they are. We are reducing them a bit. Okay? So that's the idea of logarithmic transformation. We don't want to take the frequency of the values. Last time we talked about representing the textual features, right, by their frequencies. So we don't want to take the raw frequencies, the number of counts as it is. Usually we take the logarithm of it because it's not, the importance is not linear. Okay, as the number of occurrences of the word in the document increases, the importance is not linear. It is actually something like logarithmic. Okay, so this is useful for textual features. When we have the counts, instead of using the counts as they are, we just take the log of them. Now, why are we adding 1? Yes, because if this value is 0, we don't want to do log 0. Okay, so it will be log 1, which will be 0. Okay, but log 0, it's minus infinity, so it would be problematic. That's why you are just adding 1. Okay, any question about this? Can I talk about this also for 2 minutes? Do you mind? Okay, let's stop here and inshallah continue next time.